Okay. So I'm Jérémie Mouginot. I'm working at University of California, Irvine, with Eric Regnault. So, well, you all know what Eric is doing. So basically, I'm doing the same, working on a large-scale data set with velocity maps or mainly velocity maps. So here I just copy and paste what was on the website for the calving workshop, and I just copy and paste was really linked to remote sensing. Um, and I'm not going to try to answer all of these questions because there is a lot of processes that actually are really difficult to capture from space or airborne. So I'm just going to focus on few on basically what we can measure at large scale with high enough resolution so it can be useful for Kelvin, for example. So just to do a difference between, we often now speak about big data, so I copy and paste again this sentence from Wikipedia. So it's basically, we call big data set that we cannot analyze or manage from directly by hand. We need like processing techniques. So that includes the data from Colombia, where I think, well, I'm sure there was a lot of data that were, calibrated by hand, or so there was still like someone that processed the data behind, but the data set became so large that we need new techniques to analyze that. So here, the large scale data set are big data, but all big data are not necessarily large scale. So here, what means large scale data set is referred to data that cover large regions and at relatively high resolution, which is probably not always the case, like for the bed topography. So here I just focus on this coverage of large region at relatively high resolution, which is usually done so by airborne or spaceborne data, what we call remote sensing data. So what can we do from space or from the atmosphere, from air? We can look at the geometry of the ice sheets, the surface and the basal topography. For example, the boundaries of like the ice front or ice mask and grounding line. And something that is relatively easy to do is to measure velocities on a really large region and to measure ice thickness changes. There is something that is still, it's amazing because if you look at for example, other planets, we have like awesome DEMs of Mars, much better than on Earth. So I feel like there is still a really huge gap on, for example, doing regular DEMs over large regions. So locally, we have good DEMs. Even on Colombia, it was mentioned that there was only like 2 full coverage of Colombia, which seems pretty amazing today. But here I will talk about measurements realized from optical and radar sensor. So this is like the 2 main source of data we have from airborne and spaceborne data set. So here, this is a list of mostly free data that everyone can access. So you all know the MODIS data, which is a sensor with a medium resolution between 250 meters and 1 kilometer resolution, but that acquires data every 1 or 2 days. So for people that wants to track ice front at relatively low resolution, meaning you're not gonna capture small calving, it has to be really big calving event. This is one sensor where we should look at what it has been done already, but maybe more like on a regular basis. After, there is also a huge source of data for Colombia also. It was Landsat that is much more precise. You can get a resolution to 15 meters to 100 meters, depending on which sensor you're using. The old sensor, you get a resolution closer to 100 meters. And basically, if you're lucky, you can get data every 16 days, but well, it usually never happens, or especially on Antarctica and Greenland. So I would say that here you can track what is going on monthly to yearly, so every year or every month. And there is some places where there is actually, like East Antarctica, there is not so much data to build the time series from Landsat. There is the Aster that provide DEMs and that we can use also to track features or do the same kind of track boundaries like the ice front. Or so this sensor has a resolution similar to Landsat, and now there is all this high resolution sensor that acquired actually stems, so it's really small region, but that really high resolution. So the QuickBird worldview, like they have, I think, a resolution of 30. Some of them have a resolution of 30 centimeters, and for spot. But this data are really difficult to obtain on a large scale. Like you can have a proposal or something where you acquire it for a small region, where you get like with this kind of data, usually you get serial images, so you can do really high resolution DM. But it seems so far really difficult to cover large region from this really nice sensors. So there is for people working in the US, there is now this website is just there. Like, I tried to click, it didn't work, so I'm not gonna do that. So there is I think it's maintained by Paul Morin, that US have access to really a ton of data from QuickBird and WorldView, and they're all on a website, and there is really a lot of stereo images, and well, I think I have a picture later. The coming sensor, so there is a really nice sensor that will come in 2 years, I think. No, 1 year now, Sentinel-2. So there will be 2 satellites, Sentinel-2A and 2B, and this is an optical sensor similar to Landsat with 5-day repeat cycle. They have an open access policy, meaning everyone can access the data. I guess you still have to submit like a short proposal, make sure like you're not, I don't know, a terrorist or something like that. And I think this kind of sensor will be really useful in the future. And I also want to mention this website maintained by Yano Watt, so Rapid Eyes, where he did define like a region of interest, and he posted like all this kind of data geocoded on this region of interest. So if you click, for example, on Jakob 7, you can have all the optical images, well, maybe not all, but really a ton of optical images collected over this region. So there is, and there is the same in Antarctica. So there is, it's not everywhere, but on Celtic Glacier, there is a really nice or archive actually that is maintained and updated by what. So what can we do with this optical sensor? So with the medium or poor medium resolution and quite like poor, I say it's not like every day or like what you could do with a ground-based camera. It's so like monthly you can, or with MODIS daily, you can get the position of the ice front and capture calving events and evolution of the ice front. So this has to be done, by example, Seal et al. In 2011. I don't know if the data are publicly available, but here, so it did track all the ice front in Greenland. So here it's a ton of different glaciers around Greenland, where you can see the evolution of the ice front between 2000 and 2010. So I'm sure this is like a huge database for people looking at calving evolution. And this is like something really large, so you can maybe find, or I'm sure it's what they did, you can find some region with different kind of retreat pattern or seasonal evolution. There is also a few Landsat tracking of the ice front that are I know this one is at NSIDC, so it was done by Joe McGregor. So this is in Adamson-Sea sector. So here you can see the evolution of the ice front from the 70s to I think 2000 11 or 12. And you can see the evolution, the retreat of the main ice tongue of Thwaites, or the evolution along the Croissant ice shelf. So I believe that this kind of data set are not like fully utilized by people doing modeling, and I'm sure they're really useful. And also, so about the really high resolution imagery to the world view, I found a presentation from David Sheen at university that is working with Ian Jogging at University of Washington, and he had this this view of the Earthsheet. So all the small square are images acquired by this high resolution sensor, and all the blue that are here, so it's dark blue, they are stereo images. So I think there is a huge potential, well, I guess for you as funded researcher, but there is a huge potential for mapping more regularly the DEMs, for example, of the critical region, and try to follow what is going on the ice front and all the Kelvin. And this is an image that was in the news where it's a DM of Thwaites glacier made by David Sheen, where you can see really interesting features like crevasses are really close from the grounding line of the eastern ice shelf of Thwaites. Here, this huge rift that opened in the pasture. Here, there's actually a crack here, so all this portion actually had calved. So you can see that. Well, I think it's really, this is some kind of data that I'm sure will be useful for modeling. And now, so the radar sensor, which I'm more familiar with. So you can do the same kind of tracking of ice front position and large calving event, but you also have, well, you can get velocity from optical sensor, but they tend to have less correlation, and so your velocity field is less complete. So here, usually we use a radar sensor for glacier velocity, and as we saw this morning, and I'm sure we're gonna see later on different talks, glacier velocity or a fundamental control on Kelvin range. You can calculate the strain rates, and I think it's one of the critical measurements you can do to really capture how Kelvin are evolving. So what I said, you get the background image. You can well, no, this is the same. Okay, and there's something. It's like usually it's not true for every sensor, but the resolution of velocity maps is about 300 meters. I mean, it can vary to 200, 500. Depends how you process your data, but you're not gonna capture, like, imagine we had a really, like, every minute we had well, it's never gonna happen, but every minute we had a velocity map. Even with this kind of really dense series in time, we will not be able to capture small calving events that occur on a Columbia or Tidewater Glacier in Greenland. So well, I will come to this point, but I think that for Greenland, where calving tends to be much smaller than what we're seeing in Antarctica, there is some limitation from the remote sensing data that are acquired here. So usually at global scale, where I think the best we can do, it's like one coverage per year, and even that, it still remains really difficult. So I was thinking about getting a full coverage all over Antarctica every month or something that it's not doable at the moment. There is not enough acquisition. It's not just about processing. So I think it's not going to happen soon. But locally, as for example the study from Adrien, where he has like data almost every 11 days on a glacier, that's it's doable, and will probably be more will happen more and more. Okay, this is the sensor, the SAR instruments that are available so far. So the first 5 sensors are dead right now, but they acquire data back to 92, and actually I think there is really still a lot of work to do to process. Again, there is a large amount of data that have not been processed, and that could bring a longer time series on a lot of places. So there is a new sensor that are so each sensor has a different characteristic. Basically, C-band or like the uh, it's like L-band. It's gonna collect everywhere, so you get really nice map. But they tend to have what actually there was only one, so now there is no more L-band sensor. We're waiting for EOS2, that is L-band, that will also give a really nice coverage, but now they move to like a private way of delivering data. So we're just gonna get data through proposal, which means like 100 scenes. So basically, you can study one glacier, and that's it. And there is this new sensor, TRSRX, that is X-band. And tandem that is just like it's like 2 TRSRX. That's what tandem is flying with in close flight configuration with TRSRX, and they can actually do DMs at the same time that you get the SAR data. So this is a really nice sensor. There is Cosmos Chimed. It's an Italian sensor. It's almost impossible to get data. And there will be Sentinel-1A, so from ESA. And this one is actually like Sentinel-2 that is optical. This one is as an open access data policy, which make it like a really nice sensor. And hopefully, which doesn't seem to be the case, they will acquire a lot of data on the ice sheets and on the glaciers. Well, so now this is, so previously was basically the raw data, and now it's like the velocity data that were produced. So there is a nice mosaic at NSIDC produced by Jan Jogging. So that cover from 2000 to 2010. So this is like the large scale, like this one mosaic from Radar-Sat-1. And more recently, there is this like this new product where there is much less coverage, but where there is coverage is at higher resolution, and you get more temporal resolution. Like sometimes there is 3 or 4 acquisition per year, or even more, which makes really nice to actually study calving and change, seasonal change, and all this kind of stuff. From Antarctica, which is much bigger, this is one example, like on Jakob 7. So to show the temporal variation on the Jakob 7 glacier. So you get the much smaller spatial resolution, but much better temporal resolution, which makes it a really nice product. So all this data, or probably almost all of this data, are available at NSIDC, and I encourage you to try to work with that. From Antarctica, so was the Eric Vigneault project. So we did map the Antarctica, almost full maps of Antarctica, which correspond about to IPO years, so between 2007 and 2009. And we also have this 2 product, which is so from Radar-Sat-1 and Radar-Sat-2. So this is only the interior of the ice sheets, but it's only 1 year, so you can track changes between the 2 maps. And I mean, it's not complete, but it's also a product that is available at NSIDC. And right now I'm pushing to get that online. So this is the Admutsensi sector, so I have more years than that, but I'm gonna first release this. So there's gonna be a time series spanning from 96 to 2013 or 12, I don't know. And in the coming years, where I'm more happy with the other years, there will be like one map every year from 2000 to 2014. And also there's data from 92. So there's a really nice time series. So what from this NASA project, what will come in the coming years? So there, I think Jan, I don't know exactly when Jan is in project, but I think it will continue to acquire pterosaur data and provide on selected glacier continuous acquisition. And I also know that there was like a full map from Radarsat in winter 2013, and there was also a full map made by Radarsat 2 this winter. So Jan, I don't know if this data has been delivered to Jan and if he will process that soon. And I think this data were part of what they call the Polar Space Task Group, which bring all the space agencies together to make sure to try to get data over the ice sheets. So this Radarsat data should be available for everyone at some point. The raw data, I mean, for Antarctica. So we also try to get time series on selected glacier using pterosaur or other kind of other data set. But we not. I think Jan has to pay to get access to pterosaur, and I think Eric is not willing to do that so much. So I think we're not going really to make sure we're gonna acquire like every data on some glacier. But we want to reprocess the old data. So having a map from 96 or and 97 from Radarsat, and reprocess the full. There is a full coverage in 2000 from Radarsat. That's the point. That's something we want to do for the new project. And there is a full coverage from Radarsat 2 that has been acquired in 2013. And right now we're working, Bernd, my colleague, is working on a time series of the peninsula, so mainly Larsen B and Larsen C, that's going to span from 92 to 2013. Okay. I talk about pterosaur and TandemX, and I think for carving actually it's really a great sensor, because if you acquire TandemX data, so just with one pass you get the DEM, and if you ask for 2 consecutive passes, you can measure the velocity. So that is here. So here there is a glacier going downward here, and here there is a huge crevasse. I'm not sure it had a curve already, but at least it's a huge crevasse. And here there is like all this shear zone with like ice melange on some region and a lot of crevasses. So and here, so you can measure the velocity because you have like 2 passes, and here you can also you have the topography that corresponds exactly to your velocity field, which I guess makes like if you want to model this kind of region, makes everything easier if you have the good geometry. Well, this is about the Antarctic Peninsula. So well, you all know that this region has changed, so we are planning on trying to get a full, like almost every year, a mosaic of this region. So here, this is like some kind of preliminary result we have on the Larsen Sea with from Radarsat and ALOS, and this is the kind of coverage we will get. So again, it might be difficult to use. There is still some gaps. There is not always data everywhere, or there is issue with the correlation. But this is what we're gonna, I think, release in the coming years. So what can we do with this kind of data? You saw this example this morning from Doug. This is the work from Chris on Larsen B. He used the Radarsat 1 data, velocity plus a lot of other stuff to calculate the damage on this ice shelf, and has this nice picture where you could see that there was damage along the front where actually a calving was observed later on. There is this paper from Jan, for example, where this is on a Ross ice shelf, where you can see the rift forming close to this. I don't remember the name of this item, this ice rise. So, and here you can see the rift. So this is something that's gonna be in the velocity data, and that we can try to track over time, see if there is some kind of like regularity in the calving on this big ice shelves. Um, this is something. So this is the two data sets that were released by NSIDC from dataset, so between 97 and 2009. And here you can see, so there's some portion of the shelf that are accelerating, but are still not, the calving is not fully done, basically. So here there's this portion on Filchner that seems to accelerate about like 100 meters per year, more than the ice shelf. So here it's like difference between 97 and 2009. So basically nothing is moving. There's this well-known deceleration on the ice stream. I don't remember the name of the ice stream, but and also this portion that is more interesting for us, where you can see like a calving occurring on the ice shelf. This is my work I have done on Thwaites. So here we cannot see so much, but this is our Landsat data, a mosaic from Landsat data on Thwaites. Here there is the ice tongue. There is like an iceberg just here, and here there is a rift between the two, but it doesn't seem really open, or it seems like quite strong. And all this region is full of iceberg or ice, and now we jump from the MODIS data. So this is something you can do with MODIS. So here it's all on NSIDC. So it spanned from 2002 to 2014. And what you can see is at some point here there is the reef that formed almost up to the grounding line, and after all this ice tongue that just called and went away the bay. And there's another interesting stuff. If you look at the I'm going backward. This is cool. So here, if you look at the first images, there is no rift here on the eastern ice shelf close to the grounding line. And as the glacier move and speed up, the main tongue speed up. It's gonna pull the eastern ice shelf, and there's crevasses forming just at the grounding line. So it's not gonna form a calving event right now. It might in I don't know 50 years or something, when it's gonna be closer from the ice front. But this is in terms of damage and like process of weakening the ice shelf and everything. I think it's something really interesting to look at. So here you're gonna see when the rift form, after you get a huge like calving just there, and after this seems to heal because there is no coupling anymore between the ice tongues. So as they move on the last year, it seems that probably the ice melange is getting stronger in the middle. So we have velocity data that correspond to these images. This is this. So you can see this is the main tongue. So profile just there. I showed that last week. I'm sorry. And this glacier, it doesn't move like during all these years. So basically during 10 years between 96 to 2006, all the velocity are in this range. So the ice tongue is going at 3 kilometers per year. But on the other side, so here it's a profile on the other part of the ice shelf that is buttressed by some ice rest at the end, just there. So you can see that it shows a really different behavior, where you get a strong acceleration when this one was stable, and as this one accelerated a lot, this one just like the velocity just dropped and not zero, but it was pretty close. So it dropped a lot, and probably it was the coupling that just disappeared between the two as the reef formed. And here also there's no data after this line. Well, I could have put data, but this is basically an iceberg now. So all this ice tongue got cold. Well, I think this is a nice example, like Colombia, where if you want to track how calving can affect. Well, here it might be more than just the calving, but how to capture calving that was not actually in the Yanjong paper I think this is a really nice time series to look at. Something else. So if we look at really large scale and we want to characterize how much is calving, how much is melting, you can look at the flux close to the front and the flux closer to the grounding line. Apply mass conservation between the two, and come. This is the paper from Eric, and try to evaluate. So as I said, how much is calving, how much is melting. So this is something that is pretty easy to do in Antarctica because you have these huge ice shelves, and much more tricky to do in Greenland. So here with Eric, we have mapped carefully all the ice shelf using the ALOS and NVSAT backscatter map. So at a resolution of about, so we have mapped like 100 ice shelf at a resolution of about 150 to 200 meters. And we have done that for about, well, you never know what you missed, but we think it was about more than 99% of the total ice shelf and ice zone that were included. And also we used the grounding line that we mapped, and when there was a lot of retreat, we used the 2011 grounding line. So this is to measure the flux of the grounding line. So this is the total ice shelf area that is a bit bigger than what previously given, and well, and this is some numbers of how much the ice that is discharged in the ice shelf control the total ice discharge of the ice sheet. So what we use to do that, the data set, so it's just remote sensing basically. We use the full velocity map at 150 meters. We use the bed map data that was put together by Fred Well, and that include the data from Krieg Bember on the ice shelves. That was derived, I think, from the ISAT data, and I think there was some correction from the snow layer. Well, and we also recalculate the ice thickness change on using ISAT data. So I did that the same way Pritchard did that in his paper. So we did that because the way we delineate or ice shelf was slightly different from what it did, so we could not directly use. Well, we wanted to make sure the number he had at this table were the same as the one we got for our ice shelves. So we did that, and after we used RACMO to evaluate the surface mass balance on the ice shelves. Well, and we mixed that together, using actually the mass conservation, and so we could derive the basal melting from that. So this is the map. So I think it's also something that is useful for calving. It's not directly calving, but I guess where there is more melt, you need to know where there is melt and when there is no melt. Like in a region where there is freezing, it might actually seal basal crevasses and or stuff like that. So this is the melting map we got from this data, where you can see some interesting pattern. On Emery Ice Shelf, for example, you can see there is one side that is melting, while the other side that seems to be freezing, meaning that there's probably circulation under the ice shelf that is so entering water entering this on this side and exiting the ice shelf on this side. And so here the how we call that, the camemberts were done more not directly using this map, but comparing the grounding line flux to the ice front flux, and everything that is with lines like that correspond to the calving, and everything that is black corresponds to the melting. So there's like different behavior for every ice shelves, and it seems that the big ice shelves, they're not melting much, and they're mainly calving, and the fast ice shelf, like in West Antarctica, there seems to have much more melt than much more. It seems that melt is more important than calving usually. So this is the result. Well, we get some number with larger bars about the basal met, but what we have to remember is that about half of the ice sheet mass discharge is lost through calving events. This is about the same result that was reported in Nature by Matthew here. So I think it's getting pretty strong. And as I said, percentage of melting vary a lot between ice shelf, like George 6 ice shelf that is buttressed all around is mainly melting. Anyway, there is not so much way to get calving on this ice shelf, so everything is melting. And like on the big ice shelves like Ross and Ronnie, you can get like 5 or 40% of melting, and all the other part seems to be calving. So this is like the idea for Antarctica, that calving account for about 50%, so half of the ice discharge. How it is in Greenland? Well, we don't know so much about Greenland. Like Eric has this paper where he says submarine melt is between 20 to 80%, which means nothing to everything. So basically we don't know. I think it probably changed from glacier to glacier. Based on the configuration of the fjord, the configuration of the bed, the speed of the glacier, and all this stuff. But if we take the same value as for Antarctica, which might not be the case, that means it's why we should focus on calving. So and melting, because so the mass loss in Greenland would be 30% from calving, 30% from melting, and 40% from surface melt. So this was the introduction from this morning. So I'm not gonna talk too much about that. But the point was, in Greenland, in Antarctica, if you want to capture the calving event, the calving is so big, like you get huge tabular icebergs that are calving from the ice shelf. That I think the data we have are really nice to capture that. If you move to Greenland and you want to look at all these processes that here. Large-scale data set maybe not. It's what I'm saying. Yeah, maybe not suitable for tidewater glacier. You might want to look at smaller processes that are not captured here, and also like submarine melt that are, I believe, almost impossible to measure from space or airborne, or like some basal processes. Everything basically that is not on the surface will not be captured by remote sensing. So I look around, like what is going on, and I saw this new paper on crash prediction where they're doing remote sensing. This is super nice paper where they take this UAV and they have a camera, and they take some cameras along the front. So this is a Stor Glacier. So one of this glacier in Greenland where there is a lot of data. And from this data, so they have really nice picture first, but also they can do stereo images, and they get a really nice definition of the geometry of the calving front. So, and here is an example where you can see this is plot along the front of the glacier, where they actually can map the depth of the crevasses, and they can also see where there is water in the crevasses, or if the crevasses are dry. And I think this kind of data set are not large scale as the data from Antarctica, but it might be the way to actually look at the Greenland glacier with more airborne data, UAV, and this kind of data. Also, we have seen that this morning. This is something. So probably a lot of you know James Belloc. So it's the guy that is it's a photographer. He has done movies like Chasing Ice, and he has put like some cameras on different places, and this is one of the camera that he put on Stor Glacier. So I guess there is only one, so you cannot do stereo images, but you can map the ice front like for Colombia, and here I think there's there's like 6 months of coverage, and there's few days where he took picture every 30 seconds. So usually it's like every hours or every hour or half an hour. So there is a picture. So here I just took like one per day at the same time. And this is, well, I think I think this might be the way to better understand the calving than more the, well, it has to be complementary with spaceborne data, but I really feel that for a smaller glacier, like the one, and smaller calving that are occurring just there, it might be the way to actually capture the calving. This is something else from Eric. So there's one of the important processes is the melting that is occurring, the submarine melting that is occurring on the ice front. And Eric has, so here it's not going to be also large-scale data set, but I think there is no way to really do that from space. So this is one mission in Greenland where they had a boat there with a swath bathymetry, and they actually turned the swath bathymetry toward the ice front, toward the calving face of the glacier. And this is what you get here. So this is the calving face of Storrs Glacier with the bathymetry just there. And what is really interesting is you can see there is some region where actually it seems that there is no data. And what Eric told me is probably there is no data because it's like some cavities where the acoustic waves could not like come back or something, or like there was a depression on the calving front, maybe due to water undercutting the ice shelf, the glacier. Another view, so this is a view from top. I think the camera from JSBlog was probably there, capturing the advance and the retreat of the glacier. And this is also another view where you can see these gaps and the nice bathymetry that I think is really useful for probably the issue is from when you want data from the ocean, if you want to capture that, it seems really difficult to imagine really large time series where you get a lot of data. Usually it's just few points, and as Jan Fetty showed yesterday, it seems that the circulation and the temperature of the fjord is changing really rapidly, like daily. So getting this kind of bathymetry plus models and few measurements on the fjord might be really helpful to understand what is going on the calving phase. Maybe I was way too fast, but no, that's fine. We're good. So, question: what people from the model really need? Do they need like a close view on the some glacier so they can capture what is going on? Do they want a really large scale, as I took at the beginning, large scale data set, so you get the large view evolution of this huge ice masses? So in my opinion, I think the answer is different as function of the token you're looking at. So if you're more in Antarctica, I guess the data we have are fine, although it would be nice to have more like more data in time. But if you're looking at tidal or glacier, I guess higher resolution like TORSOR and ground-based observation are probably better. Thank you.